My name is Gene West. I am an engineer of High Fuels Inc. I have conducted the measurements confirming Professor Santilli's IsoRedShift and IsoBlueShift.
My name is Gino Amato. I am the computer technician of High Fuels Inc. I have assisted Gene West with the compilation of all spectrograms.
I am Michael Maravich, a building specialist of High Fuels Inc. I have constructed the IsoShift testing station.
I am Chris Lynch, a mechanical engineer of High Fuels Inc. I have assisted in the high pressure engineering specifications of the IsoShift testing station.
My name is Michael Rodriguez. I am the electrical engineer of High Fuels Inc. I have constructed the various electrical components of the IsoShift testing station.
In a paper published in 1983 by the Italian Physical Society, Professor Santilli achieved the enlargement of the Lorentz-Poincaré symmetry, today called the Lorentz-Poincaré-Santilli isosymmetry, providing the universal invariance of the most general possible interior dynamical systems. Subsequently, Professor Santilli discovered that his new invariance predicts a frequency shift of light propagating within transparent physical media without any relative motion between the source, the medium, and the detector. The prediction of the new shift was first published by Professor Santilli in 2 volumes of 1991. The first on the new mathematics necessary for the construction of the new symmetry, which he called isomathematics, and the second volume on the enlargement of Newton, Galileo, and Einstein theories for interior dynamical conditions. In view of their derivation via the new isomathematics, he called the new shifts IsoRedShift when there is a decrease of the frequency and IsoBlueShift when there is an increase of the frequency. In the same volumes of 1991, Professor Santilli proposed the conduction of a number of experiments to verify or deny these predictions, such as the measurement of the wavelength of light from a faraway star before and after passing through a planetary atmosphere, the measurement of a number of wavelengths of the sun in the transition from zenith to horizon, and other experiments. Following 2 decades of lack of interest by the physics community to conduct the proposed experiments, in 2010 Professor Santilli conducted the test on his own by achieving a confirmation of all predictions made in 1991. These results were published in Open Astronomy Journal. In this DVD we shall present the initiation of systematic independent confirmations of Santilli IsoRedShift and IsoBlueShift. Let us begin with a description of the IsoShift testing station. As you can see, it is composed of 3 parts. The first cabin here on my left hand side housing various lasers. A second cabin at the end housing the wavelength analyzers, and 2 pipes connecting the 2 cabins. One of special steel for high pressure and the other in PVC for various collateral data. As you can see, the interior of the laser cabinet contains the lasers on this table and facing the terminals of the pipes. An air conditioning unit and related duct to keep the lasers at constant temperature of about 70 degrees, and other equipment. The high pressure steel pipe initiates with a Lexan window you can see here. The high pressure steel pipe then continues for a length of about 60 feet or about 20 meters to the other shed. As you can see, the end cabin contains a second Lexan window at the end of the pressure steel pipe, plus various means of measuring wavelength, such as this wavelength analyzer. We also have an air conditioning unit and related ductwork to keep the analyzer at a constant temperature of 70 degrees Fahrenheit. We also have various recording means that are processed by our engineer, Gino Amato. A main feature of the IsoShift testing station is that according to Professor Santilli's original conception, there is no relative motion between the laser, the analyzer, and its interconnected medium inside the pipe constituted by a gas at pressure. Correct measurements of the IsoRedShift require the laser and the analyzer at constant low temperature of about 70 degrees Fahrenheit, while the pressure pipe also must be at a low temperature of a maximum of 70 degrees. According to Professor Santilli's principles, the gas contained in the pressure pipe has to be at a sufficiently low temperature to assume all of its atoms in the ground state. Under these conditions, the energy needed for the interaction is provided by light, resulting in the increase of the wavelength with the consequential redshift. Under these conditions, the energy needed for the interaction is provided by light, resulting in the decrease of frequency with consequential IsoRedShift. Correct measurements of the IsoBlueShift also require that the laser and the analyzer be at constant low temperature of about 7 degrees Fahrenheit, but the pressure pipe has to be at a sufficient high temperature of at least 130 degrees Fahrenheit. According to Professor Santilli's principle, the IsoBlueShift requires that the gas in the pipe be at a sufficiently high temperature so that its atoms are in excited state. Under these conditions, the energy for the interaction is predominantly released by the excited atoms, resulting in an increase of frequency of light with consequential IsoBlueShift. Acceptable measurements for an IsoRedShift are done at night or early in the morning due to generally high temperatures here in Florida. We first compress in the steel pipe a gas up to 2000 psi or about 166 bars via this compressor, and then verify that the laser and the analyzer and the pipe are at a maximum of 70 degrees. When we then measure and record the wavelength of the laser light coming out of the terminal Lexan window with the pipe at 2000 psi. We then remove the gas in the pipe as fast as permitted by safety and pull a vacuum on it with this pump. After verifying that the laser and analyzer have remained with the original temperature, we measure the wavelength of the laser light through the pipe at a vacuum. Comparison of the two measurements clearly show a measurable, systematic, and reproducible shift toward the red of the wavelength at pressure compared to the wavelength under vacuum. Since the red shift occurs without any relative motion between the laser, the analyzer, and the gas inside the pipe, the measurements confirm Santilli IsoRedShift. Note that we do first the measurements
at pressure and then those under vacuum in order to minimize the lapse of time between the two measurements. In fact, bringing the pipe to pressure requires such lapse of time to cause significant climatic changes with consequential loss of accuracy. The measurements of IsoBlueShift are done during the day when the pipe is exposed to strong Florida sun. We then follow the same procedure as that of the IsoRedShift, namely, we first measure the wavelength of the laser when the pipe is at pressure and at about 130 degrees Fahrenheit. We then empty the pipe as rapidly as permitted by safety and pull a vacuum. We measure again the wavelength of the laser propagating under vacuum and compare the two wavelengths. Under the indicated conditions, we have seen a systematic shift to the left of the wavelength of the laser at pressure and at temperature compared to that under vacuum. Therefore, these measurements confirm Santilli IsoBlueShift. We have also done a third type of measurements as follows. We first measured the wavelength of the laser with the pipe at pressure and at low temperature by measuring an IsoRedShift. We then keep the pipe at pressure and wait until the sun is at the zenith to achieve maximal temperature of the pipe while continuing to monitor the wavelength of the laser. During these measurements, we have seen the wavelength change from IsoRedShift to the IsoBlueShift, thus necessarily passing through a no-shift value. These observations confirm Santilli's no-ISO shift, in which energy loss by light is balanced by the energy released by the medium, resulting in no measurable shift. The measurements of the no-ISO shift are important to prevent possible erroneous repetitions of the measurements with claims of no shift that would be quickly disproved by experts in the field.
Let us now review Professor Santilli's original measurements of IsoRedShift. Professor Santilli's main objective was to establish that the redness of sunlight at sunset is due to a violation of Doppler's law within our atmosphere, since the redshift occurs in the absence of relative motion between the sun and our Earth. He argued that the sky is blue when the sun is at the zenith because red light is quickly absorbed by our atmosphere, thus leaving blue the only penetrating light in our atmosphere, as it is the case also in water. Consequently, Professor Santilli argued that if red light does not reach us for the short vertical trajectory, it is impossible for red light to reach us after traveling in air for about 10,000 kilometers. The sole possible interpretation of reality was therefore that blue light was redshifted during its long travel in air without any relative motion, and called this effect IsoRedShift for certain technical reasons. Professor Santilli dismissed the old conjecture that redness at sunset is due to the predominance of the scattering of red light over other frequencies due to the impossibility for red light to reach us at the horizon. In any case, the scattering conjecture is not applicable to the case considered by Professor Santilli, which is the redness of the sun direct sunlight at sunset, since scattering does not exist along a straight line. In spring of 2010, Professor Santilli built the IsoShift testing station and initiated systematic measurements of IsoRedShift with the technical assistance of known U.S. laser experts Kevin Kay and Brian Rogers, as well as other technicians. Note that the main objective was to prove the anomalous redshift of blue light in our atmosphere at sunset. Therefore, Professor Santilli was forced to use a blue laser light and air as gas. For this purpose, he purchased a 400 microwatts blue laser as shown in the picture and passed through mirror the laser light at the exit and then into the wavelength analyzer. As indicated earlier, he measured the wavelength of blue laser light when the pipe was empty, then at pressure, and compared the results. The picture presents the first experimental evidence of Santilli IsoRedShift obtained on June 27, 2010. This evidence was then confirmed by several additional measurements. This picture shows the increase of the IsoRedShift with the increase of pressure of air in the pipe. Since the increase of pressure under the same length is equivalent to the increase of length under the same pressure, the latter measurements establish that the IsoRedShift increases with the increase of travel in air as it is visible to the naked eye. It should be indicated that Professor Santilli only wanted to establish the existence of the IsoRedShift and not its value for a given pressure of air in the pipe due to the clear preliminary character of the station. Following systematic confirmation on the existence of the IsoRedShift, Professor Santilli released a paper for publication in the Open Astronomy Journal. This paper clearly predicts the IsoBlueShift, although Professor Santilli did not try to measure it because calculations indicated the need for high temperatures requiring special equipment. The indicated paper also predicted the no IsoShift as a necessary intermediate step between IsoRedShift and the IsoBlueShift. We initiated our independent verification of Santilli IsoShifts in early June 2011 and continued measurements through mid-August 2011. We improved the accuracy of the original measurements by Professor Santilli by eliminating the mirrors and placing the analyzer directly in front of the exit window. We then assured that the blue laser and the spectrometer were kept at constant temperature of about 70 degrees Fahrenheit via ducts from the air conditioning units as shown in the pictures. Next, we discovered, mainly by accident, since it was predicted but not expected by Professor Santilli for the available setup, the transition of the shift with the increase of the temperature from the right to the left of the base wavelength in vacuum. This is illustrated in the picture of June 15th, 2011, which is the first evidence of Santilli IsoBlueShift to our knowledge. Consequently, we set rigid standards for the measurements of the IsoRedShift, requiring the pipe at a maximum of 70 degrees Fahrenheit and the IsoBlueShift, requiring the pipe at a minimum of 130 degrees. In both cases, with the laser and analyzer at 70 degrees Fahrenheit. The following three spectrograms show representative cases of IsoRedShift obtained under the above conditions, showing values of the shift of the order of about 0.05 nanometers, although with decreasing value due to temperature increases. The subsequent spectrograms show corresponding IsoBlueShift, also for different values due to variations in the pipe temperature. These additional spectrograms are currently under investigation due to the double peak, one redshifted and one blue shifted. We should finally note that our measurements leave open the possible correct value of the IsoRedShift measured by Professor Santilli. In fact, Professor Santilli's first measurements showed an IsoRedShift of about 0.5 nanometer, while our measurements show an IsoRedShift of only 0.05 nanometer. However, Professor Santilli's first measurements were done in the winter with the pipe at low temperature, while our measurements have been done during the Florida summer with 70 degrees Fahrenheit being the lowest possible temperature of the pipe. To resolve these different values, we plan to complete the pressure pipe with suitable cooling means to bring its temperature down to freezing temperature and repeat the measurements at that temperature. Even though we are not in a position to provide exact numerical values of the IsoRedShift under given conditions, we can safely confirm that Santilli's IsoRedShift clearly increases with the decrease of the temperature of the pipe under the same trajectory of the laser and the same air pressure. Needless to say, we encourage all possible additional independent verifications by interested scientists, since there is so much still to be understood and measured.
Upon completion of the preceding measurements of the IsoRedShift and the IsoBlueShift, we conducted a second group of experiments aimed at the experimental confirmation that redness of the sun at sunset is due to Santilli's IsoRedShift. For this purpose, we set up equipment here shown consisting of a conventional telescope converging sunlight into the analyzer, capable of detecting a band of wavelengths from blue to green. We then first measure and record direct sunlight when the sun is at the zenith, as done here. We then measure and record direct sunlight when the sun is approaching the horizon at sunset. Unfortunately, we could not measure direct sunlight when the sun is actually at the horizon because our telescope provides spectrograms excessively dim for accurate measurements. In fact, when the sun is at the horizon, there is need for large parabolic mirrors to converge sunlight into the analyzer. These measurements are contemplated for conduction at some future time.
Today is Wednesday, August 3rd, 2011, and we are at beautiful Sunset Beach in Tarpon Springs, Florida. This is the location where we capture the measurements of the direct sunlight at sunset.
As stated before, the light below around 20 degrees above horizon is too dim and too small for us to measure accurately. This telescope and analyzer are the equipment we use, also the computer to capture the measurements at sunset.
Is it an emergency? Is your son? I'm not yelling, I'm talking. Is it an emergency?
In this and the following spectrograms, we show in the top sunlight from blue to green when the sun is at the zenith, and in the bottom the same light when the sun is about 30 to 10 degrees from the horizon. These spectrograms show a clear, systematic, and repeatable IsoRedshift on the order of 1 to 2 nanometers, even though the sun shows no visible redshift at all. It is then evident to expect a progressive increase of the IsoShift with the decrease of the angle of the elevation. Despite their preliminary character, our measurements do confirm Professor Santilli's IsoRedshift origin of the redness of the sun at sunset. In any case, we should keep in mind that such origin is the only possible one due to the impossibility of using any form of scattering for the case of direct sunlight. Needless to say, we encourage all possible additional independent verifications by interested scientists, since there is so much still to be understood and measured.
We conclude our presentation by reporting a third group of measurements we have conducted with the same blue laser light and the same wavelength analyzer used for the preceding test, but in a different experimental setup. The objective has been the measurement of the wavelength of the blue laser light when reflected by a polished aluminum surface at increasing temperature. As one can see, this is the laser, this is the reflective surface, this is the analyzer, and this is the torch applied to the back of the aluminum plate. Systematic measurements conducted at various times have established the absence of any shift in the reflection of light under the above conditions in the transition from ambient temperature of the order of 80 degrees Fahrenheit to about 300 degrees Fahrenheit as shown in the spectrograms. This result is presented in the hope that theoretical physicists may study its possible implications for the scattering of light, since latter phenomenon is still significantly unknown.